having me. Yes, thank you for having me here. And I'm sharing my screen. I hope you can all see my slides. Yeah?
Yeah, we can see it.
Thanks, Mark. And yeah, I work at Unitary Fund, which is this non-profit working to make the quantum technology ecosystem as open as possible. And I titled this talk "Updates from the Quantum Jungle" because there is a very nice talk given by Will Zhang, the president of a nonprofit, that you can find on Unitary Fund YouTube channel, where he's introducing this concept of a quantum jungle, where we are, where this is not an environment where things are siloed, but things interact with each other, just like in a jungle, and we're helping filling the gaps at Unitary Fund. So yeah, let me share and let me give a brief outline of this talk. I'm going to introduce the Unitary Fund. Some of you may not be acquainted with it, and speak about the main community project that we are working on. There are microgrants that we provide. A recent event that I want to speak about that really got us excited, Unitary Hack, and then there are other supported projects that we work on. And then I wanted to talk about the in-house research that we do with this error mitigation toolkit called Mythic that we're developing with a wider community. So Unitary Fund is this non-profit entity that is supported by a series of organizations, some of which you see also listed here, and also thanks to grants that it wins. So it has both like private and institutional sponsors. And on the right here, you can see some of our partners for some of the projects, such as Department of Energy funded multi-year projects that we perform with academic partners. And we are focusing on open source software because being the aim that of making the quantum technologies ecosystem as open as possible, that's a way that we found to have the most impact in a scalable and efficient way. So this is a brief overview of the team. I mentioned before Will, who's the president and founder of the Unitary Fund. And here are my co-workers. Actually, I should have used another slide. So this is the old slide, and yes, here it's the update. Here's the update. So there's Will, and now there's like 2 new members, which are Dan Strano and Vincent Russo, joining myself, Andrea Mari, Sarah Kaiser, and Ryan LaRose. They're all experts in their own, in different parts of open source software development in quantum science and technology, and with a specific expertise in quantum computing. So that's the core team, the technical staff. And then there is an advisory board, which is formed of 15 volunteers, experts in quantum systems and software, coming from leading institutions and companies that help review the community activities that we organize, such as the microgrant program, or in collaboration with the Quantum Open Source Foundation, the Btec prize. And yes, and about the microgrant program, this is a no strings attached, no heavy bureaucracy program where explorers in quantum technology can ask for $4,000 grants to help make the ecosystem more robust, and more effective. So sometimes it's a solo project, sometimes it's a small team, sometimes it's a larger team, and most of the times these are folks working with open source software, but that's not the only case. I will show also examples where that is not the case. So far, we've given almost 50 grants in 21 countries. These have led to research papers, but also open source software that is well maintained. And yeah, I'm citing here some stats from GitHub. If some of you are developers, may know these database and social network, sort of like a repository where you can keep code that is open source. And there are more than 6,000 commits in projects that were awarded microgrants, and sometimes were projects that started as a microgrant. And there's also like some startups and even a new non-profit organization that started. And all of these, it's a little bit more than 100K. So it's a small microgrant that is given each time, but we think that is a really big impact, because that's on average, like if you see like at the, not the net cost, but gross cost of a couple of PhD students, maybe for an institutions, and you're seeing this really amazing activity in many directions. So that's part of like the more community programs that we have. I will also speak about Unitary Hack and the support we're giving to our other projects. And then there is Unitary Labs, the technical stuff that I presented in the previous slide. And that's where we develop things that we don't find in the community. And sometimes it's usually it's like more long-time projects, as well as supporting established projects in the ecosystem that may need specific support. So here I'm providing like the two main projects that I'm involved with. One is Mythic, which is this error mitigation quantum compiler that we're developing at Unitary Fund. And it's built on original research. It is an interface so that it can be used by as many users and researchers as possible, which means that it does integrate with existing open quantum software stack. I will give more details about this and also explain what error mitigation is. But in brief, it's practical quantum error correction that can make existing noisy intermediate scale quantum computers more precise than how they would perform if you were not applying this layer of mitigation techniques. Another is QuTiP, the quantum toolbox in Python, which is a really popular project that started well before I joined it first as a user, as a contributor, and now as one of the admins that is helping maintain the project and also stir up a community around it. So about the microgrants, I wanted to give just a quick overlook of outlook, sorry, of what we have been founding, and it's quite broad. So here on the left you see QREC, which is an open source simulator by Dan Strano and collaborators, and I'm really happy that Dan joined the team recently. That is has an amazing performance that was beating the state of the art. You see here in a plot beating like leading providers with their own simulators, and it's specifically designed to work with multi-threading and GPU accelerated parallelization. Another project by Steven Diadamo and others, it's QNetSim, which is actually a simulator of what will be like, the prototype of an early quantum internet. So just as ARPANET was made of a few nodes interacting with each other, and you see these plots on the stretching over the US in like I think the late 70s, something like that. Similarly, folks are testing and deploying these quantum internet networks, and one thing that is very important is like to simulate on a computer, so not only like in the on-field deployment what's happening, how this protocol works, but also like providing a physical layer. And then another project I'm showing here, it's OLSQ by Daniel Tan, which is really a toolkit that allows to compile with benchmarks that are performant and comparable, and sometimes better than state of the art. So this is like a table taken from a paper by Daniel and collaborators, and they take what is right now one of the standards, which is toolkit developed by CQC, and see that the tool that they developed, benchmarking it against a problem that is used as a benchmark, which is QAOA, this hybrid classical quantum optimization algorithm, is performing very well. As I mentioned, the microgrants are not only for open source projects, and they can in general be related to opening up the access and the community that is building quantum technologies. So these are three examples of community-focused project that we funded. One of them is QWorld, which really has been for me like a surprisingly successful series of events in many directions that were like very surprising, starting from Eastern Europe and then joining more and more countries. And now QWorld is a non-profit itself. That's and you see here in the bottom left some of the stats of their activities. That's up to like a tour that they made in 2019, where it was possible to do seminars and workshops in person, but they also had a very successful online remote-only webinar series and summer school. There is Gate 42, which really put quantum computing on the map in Armenia, and was done by a collective of researchers. And then there is a project that was actually started by a student. I think she was a bachelor student, Lia Ye, which is a full stack quantum computation, and also the related Universal Quantum Education Discord channel, which is an aggregator of opportunities that are out there in quantum computing, and more in general in quantum technologies. So it's really driven by young students, and that's really really inspiring. So another metric that it's highlighted is the work that Unitary Fund is doing for workforce development. And Tuali is from the Congo, was studying in India, and used the Unitary Fund to help develop Avalon, which is this quantum programming language that he wrote. And this was like the first thing that got him into open source quantum computing. And then now Tuali is a quantum software engineer at Zapata Computing, one of the most successful startups out there in quantum. And he's also like a Unitary Fund advisory board member that is now helping us review applications and also mentor new projects. Petar instead is another example, took up quantum computing as a hobbyist, and then the quantum computing studio that was funded, quantum programming studio that was funded thanks to a Unitary Fund grant, that was the stepping stone of what became a venture capital funded startup named Quantastica. And I also like to look at these sort of like network effects that start happening. So these are two projects that have been funded by Unitary Fund. One is Yao.jl, which is a toolkit to design quantum algorithms in Julia, which is this scientific focused, very modern programming language. And another one is PyZX, which implemented some, was one of the first, actually, I think the first open source program to implement ideas from ZX calculus through diagrams that can help compile better in an optimal way quantum circuits. Well, these two projects that were both funded by Unitary Fund sort of like interacted, actually the folks involved. And in summer 2020, Yao Lang, which is the domain-specific language for Yao.jl, released the support for ZX calculus because it was inspired by PyZX. And actually talking about PyZX, I took this image from a paper in Physical Review X, which is a high-impact open access journal edited by the American Physical Society, from actually other researchers, mainly based in Japan, who started using this software. And as they cite for the results, and as they cite in this part that is highlighted, they really say that it was really important for them to make the study efficient, not to reinvent the wheel and use PyZX as a tool to build on with new science. And I think that's what's really exciting about open source. It's this in a scientific setting, and especially in quantum science and technology, is this collaborative approach. So I want also to give some stats about the microgrant program, something we got very recently for the end of our second quarter. So we gave 12 new grants in 2021 to folks from 8 countries. And there were 4 new publications based on these open source projects. And yeah, I here wanted to show that about a quarter of the people that receive the grants are based in the US. There's let's say a strong outpost in Europe as well as Canada. I must say it's the second most represented country, but then it's really reaching other continents. We'd like to do more both in South America, Asia, Africa, and yes, and we're working on it, and we'd like to reach out to this community. So if you have ideas, this is something we're working on, but please do get in touch also with me at nathan@unitary.fund about this. And I also wanted to point out that QuTiP itself, which is, it's a project that existed for much more time, as sort of like 7,000 commits, and commits are not everything, but these mainly new projects that have been funded by Unitary Fund have around like 6,000 commits. So things are starting to be kind of like comparable. And there are some other stats that we got from actually sending a survey to grant winners. And folks were really happy about their experience. And it's kind of like a diverse way through which they got to know about Unitary Fund. We'd like to do more in terms of like gender. the gender of folks who apply. And also, we're looking at whether this is yes or no the first open source software experience they have, and it's quite impressive that about half of the participants started open sourcing their code thanks to these grants. And yeah, we want to improve on things that are like, here were like some quotes. I don't have the time to read of them all. Maybe you can like stop the presentation or take a snapshot. But one thing I want to point out is that we want to focus on more post-project support, but at the same time, from this survey, you see on the right here, there was a question about, is the funding of $4,000 enough and meaningful? And actually, folks were really there was a unanimous almost answer about the fact that funding was really important. And the $4,000 funding that we provide, it's significant. Yes, then there is this other project I want to speak about, which is Unitary Hack. I need to give credit to the Unitary Hack director, Dr. Sarah Kaiser, about really the design and execution of this event, together with our supporters and the whole team. So the concept is that there are a lot of hackathons out there. They're great. What we wanted to tailor, it was something that was already helping established projects and helping the maintainers, because you know, open source software developers sometimes are, you know, these unsung heroes of science, and sometimes they get a lot of requests about solving issues and bugs that don't work on their software. And the idea was really to get this excitement that there is in the community, and also from folks that are new to open source but would like to contribute, and not doing, you know, a new proof of concept that maybe stays idle after a while or stale, but support existing projects that already are providing value to the community. And we thank Xanadu, Dora Hacks, Pascal for their support as sponsors. And we gave out bounties on existing issues that were opened by the maintainers and flagged by them. And also, like, we gave out, you know, swag to everyone who contributed, also to projects that, also to issues that were by 19 selected open source projects that we got in touch with, but even not necessarily from issues that were already pre-flagged by the maintainers. So here's a list of the projects that were involved. Some were already cited before, so they were sort of like graduates from a Unitary Fund, such as QNetSim, QRAC, but others were like very cool projects that are out there in the community, such as Xanadu Penny Lane or XACC, developed at Oak Ridge National Lab and elsewhere, and other projects that we thought it was nice to support. And here on the right, you see this list. This is just a snapshot for Unitary Hack website. If you go on unitary.fund website, you'll find all the links, and you see all these issues that have been hacked, and so they've been solved by the community. So I spoke about this involvement. We also do run these quantum software talk series. Actually, we also run the journal club that many times is open, and we do these both on, like, the quantum software talks are on Twitch, and then a lot of our activities are on Unitary Fund Discord. You can find it by looking for discord.unitary.fund in your browser as a URL. And then it's also, like, very cool, in my opinion, that we do these community calls online on Friday that are accessible to all, again, on the Discord. Last year, Unitary Fund awarded the Btec prize for open source software, and this was like a cash prize for the motivation for another otherwise unnoticed individual for their outstanding high impact contribution to the field of quantum open source software. and the grant went to Roger Luo, who's the lead developer of Yao.jl that I spoke about earlier. And then we would like to build upon this, and one of my dreams and aspiration is like to provide sustained support also with sort of like open source science fellowships that would be year-long or even longer. And we think that these are very important, first of all, because there is the open source ecosystem on which quantum computing from a scientific and technological perspective is relying upon, really needs experts focusing on this. Many times right now, these experts work at large corporations or startups or national labs. And if they're in academia, they're able to devote some time for open source software, but it would be cool if that would be like, the main goal, and that would be at the same time a knowledge also from an academic point of view. And then there are other reasons that are more practical on why this is a kind of like robust way if you implement it remotely. Something I didn't mention, the whole team at Unitary Fund, it's fully remote. And then we would like to make something again inclusive, again with this narrative of helping folks that don't have like a formal upbringing in quantum science, or actually, sometimes ago people were not even saying quantum science, but just physics or engineering or computer science, and get into this quantum ecosystem. And then again, well, this is like kind of like related to the COVID-19 disruptions, but we think that it also highlighted some structural issues in how research is performed nowadays, especially theoretical research. Okay, so I guess my time is almost up, so I will very briefly give an overview about Mythic, and I already apologize if I have to go fast on some of the slides. So Mythic is this Python toolkit to implement quantum error mitigation techniques and help researchers and developers develop new ones using existing building blocks. And here you can see some of the stats. You can find Meetup online on GitHub, on Unitary Fund organization repository, and it has been already downloaded 13,000 times. We roughly make a main release a month, a major release a month, so we are at the 0.9 version, and it's really an amazing tool. But let me first give a motivation for it. So this is maybe the only equation I have in this talk, which is the Schrödinger equation can also be expressed in terms of this von Neumann master equation. It's a bit more general from information theoretic point of view. And usually when you write a quantum circuit, which you can see below with 2 qubits and a controlled operation and Hadamard on one of the qubit, well, this evolution, usually it's assumed to be noiseless. But the reality is that if you make the stack of gates long enough, and then you run this on any available quantum computer, in the end you'll get what it's depicted here, sort of, which is hopefully some white noise. So things become really intelligible at some point. And why is that? Well, because actually right now we have this sort of like cross your finger method. Of course, it's not just that. People are thinking about error correcting techniques to employ now. But for a long time, quantum computers were not here, not even as prototypes. So there were like ideas, and there are proposals for error correction that may work in the distant future, or maybe not so distant future, but not today or tomorrow. And then there is a series of techniques. Some of the names are quite technical, listed here. Some come from approximate error correction. Some have been developed more recently. Some involve some pulse stretching. But in general, they involve a mix of quantum sampling and classical inference that is performed on a quantum circuit, on a quantum program, and actually on multiple quantum programs that are run on the devices. And this takes the name of quantum error mitigation, and here highlighted is the first technique, which is zero noise extrapolation. That is the first technique that we did implement in Mythic. So, and this actually, it's relevant for algorithms that people are trying to implement right now, and features that such as the variational quantum Eiger solver, in general quantum machine learning applications, and gate tomography. And again, a difference from standard error correction is that in the long run, of course, we would have to go to quantum error correction, but this is unfeasible with near-term quantum computers, where error mitigation, it's usually asymptotically unscalable, but at least in this intermediate regime, it's feasible with near-term quantum computers and can provide improvements immediately, as we've shown with tests on hardware. So for the sake of time, I guess that I have to go fast on this. I just want to show you like a basic sketch of how Mythic works. So imagine that you want to run your quantum program, execute it on the back end, and then get an expectation value. And so the quantum program can be written in any of the formalism used by these program languages, or well, actually these are libraries: QuTiP, Cirq, Rigetti, or Bracket by AWS. And then you can run this on real hardware, such as on IBM Q, or a simulator such as QuTiP. The idea of Mythic is to be completely agnostic with respect to the backend, and to be really a layer that is in between. And so far we have implemented zero noise extrapolation, probabilistic error cancellation, and a technique called Clifford data regression that was developed recently at Los Alamos with collaborators. And we're really happy that some of these authors decided to contribute back to Meetup. And now we have this batch of techniques that one can use and benchmark against each other to see if a result that which one performs best with respect to a given algorithm, a given backend, and also specifics of a given algorithm, such as depth, number of qubits, and so on. Yeah, so these are some stats about Mythic. I just want, again, to emphasize that this is an effort that is led at Unitary Fund, but it happens through a much wider community. I think this is a snapshot from our Discord server that at a time where we were having sort of like more contributors from the community than actually technical stuff at Unitary Fund. It was pretty exciting, and now it's almost always this is the case. And again, we reached like 20 external contributors recently thanks to Unitary Hack. So yes, I don't have time to go through these zero noise extrapolation methods and the details of these methods. I apologize with you all and Mark for putting too much stuff here. I just want to point out that recently we integrated with Bracket together with Cirq, QuTiP, and PyQuil, also with this technique that is probabilistic error cancellation, which relies on tweaking a bit the quantum circuits that you run in a way that will allow you to then infer what the ideal gates that your machine cannot perform actually would be, and correct for this error. And yes, and the last two things I want to say very quickly. We are involved also in supporting other projects. One of them, as I mentioned, is QuTiP. And recently, QuTiP, as a design choice, split up the core functionalities of simulating the evolution of quantum circuits with, for example, with respect to others such as optimal control and quantum information processing into different sub-packages. This is a recent paper, white paper, with respect to the QuTiP QIP sub-package And here is a white paper that was recently put online, and it's really bridging the quantum circuit formalin that you see here on the top with actually what happens behind the scenes when actually things are implemented on a quantum hardware or when they are simulated. And here you see the pulse level description on different simulated processors such as spin chain model, superconducting qubit model, and optical control model. And again, I think that Unitary Fund is also helping QuTiP grow as a project, where are more release, where is a healthier ecosystem, developers meeting more regularly, and we also establish a governing board for the QuTiP project, which is itself done open source. Another project that it's kind of like similar to this QuTiP QIP module is Pulsar, which is actually a simulator for atomic arrays. And this is somewhere where Unitary Fund teamed up with Pascal, which is this startup that is also developing Rydberg atom-based quantum computers that actually Pulsar is also simulating. And this is quite a unique simulator for at the pulse level for quantum circuits, but also beyond for like analog quantum computation and quantum simulation, because they're like in Rydberg atoms, the processor that you initialize then kind of like is destroyed at the end of the measurement. It's something really different from superconducting circuits where the processor is hardwired. And that also requires new software. We were happy with Unitary Fund to help with our expertise and develop Pulsar, which is now open source, and also took part to Unitary Hack. It will be one of the highlighted projects in IEEE Quantum Week workshop that I am organizing at the end of this year with Travis Scholten on open quantum hardware, which is also like a focus of Unitary Fund beyond quantum software, which is software to help understand and design and control hardware in the lab and at companies. So thank you very much. To get in touch, to keep in touch, go to discord.unitary.fund or send me an email.
Super. Thank you so much, Nathan. Are there any questions? Okay, so I guess we don't have any questions at the moment, but if you do think of any, please let Nathan or myself know. And thank you again, Nathan.
Thanks, Mark. Thank you.
Okay, bye everyone. Thank you.
Bye-bye.